Alright, welcome scrubs and bums and other people who are doing other things not being in discrete math class. We are going to talk about the finite projective plane. Ready? Alright, what is the finite projective plane? It's a model of axiomatic geometry. Perhaps we'll put that away. Amy, close the door. It is a system, projective plane. It is a axiomatic system in which we have precisely three axioms. Let's review them. FPP1 says any two distinct points are on one and only one common line. Any two distinct points are on one and only one common line. Okay. FPP2 says something which sounds really, really similar, which is that any two distinct lines contain one and only one common point. Two distinct lines contain one and only one common point. Thanks. Hello. And FPP3 says that there exist four distinct points, no three of which are on a common line. There exist four distinct points, no three of which are on a common line. Okay, a lot of words, there's a lot of quantifiers. Before we even fully digest this, let's talk about FPP3 prime. FPP3 prime would be, for symmetry purposes, like sort of, you could think of it as like the fourth axiom. It basically restates the information in FPP3, but like the reverse. So it says, notice, we talked about this last class, but I'll repeat it again, that FPP1 and FPP2 contain a certain symmetry with each other, right? It's like a duality principle, sort of just like in Boolean algebra. For any 2 points, there is one line that goes through them. FPP2 says for any 2 lines, there's one point that they go through. So they're like symmetrical relations. And FPP3 says you can always find 4 points such that no 3 of those points are on the same line. So the equivalent of the equivalent kind of statement with the point and line concept switched is that, well, you tell me.
4 distinct lines, no 3 of which contain a common.
There exist 4 distinct lines. 4 distinct lines. I guess we did this last class.
Yeah.
No 3 of which, I'm so tired I forgot all of last class. There exist 4 distinct lines, no 3 of which go through or contain a common point. Contain a common point. Okay. We started this proof, but we didn't really finish it. It was a little bit sloppy, so let's kind of like do it again. This time really carefully. Okay, so goal is to prove FPP3. Gossett says, well, we could have just put it as an axiom, and then it fully shows that the system is dual with respect to points and lines. But actually, you can prove FPP3 prime from FPP3. So let's do that right now. Okay. So we are going to prove FPP3 prime. First of all, we're going to start with FPP3. Okay, so this is, I think we did this exact thing, right? By FPP3, we have 4 lines, no 3 of which, no, 4 points. 4 points, distinct points. No 3 of which are on a common line. No 3 of which are on a common line. So yeah, we're kind of repeating the last 10 minutes of class, but that's okay. Okay, so let's name those points. Let's call them P1, P2, P3, P4. Okay, so what we have are 4 points, and I'm going to draw them, although I'll draw them, but the picture is not a necessary part of the proof, it's just there to help us think. So what do I know about these points? First of all, they're all distinct, because these are 4 distinct points. Alright, so if they're all distinct, then I'm just going to state very explicitly every single fact. So P1 is not P2, P1 is not P3, P1 is not P4, P2 is not P3, P2 is not P4, and P3 is not P4. Okay. And now, besides these 4 points being distinct, axiom FPP3 enables me to assert something about these lines, which are that no 3 of them are collinear. So I'll write over here what this really means is that P1, P2, and P3 are not collinear. Also, P1, P2, P4 not collinear. How many of these statements do I need to make? 4 of them, right? Because for each, it's just 4 choose 3, basically. Which is, okay, so P1, P3, P4. Those 3 points are not collinear. There's no line through them. And finally, P2, P3, P4 not collinear. Okay. Good. All right. Now, and this seems like overkill, but in my opinion, personally, when I've tried to do these things in the past, I have gotten confused when people are kind of a little bit sloppy with the proof. So I'm going to be extremely explicit about everything because I think that makes it easier to follow. Okay. So let's populate our model with some lines. So let's draw, I think we did this last time, but I'll do it again. Let's draw the line through P1 and P2. Let's call that L1. Let's draw the line through P3 and P4. We call that L2. The line through P1 and P3, we call that L3. We call this line L4. And then we also have the lines through P2 and P3. We'll call that L6, and we'll call this L5. Okay. Now, this is not a complete model. Don't think that I'm done. If you were to look at this particular arrangement of points and lines, it actually violates the axioms. For example, which axiom does it violate? Axiom 2, because, take lines L1 and L2. They're not intersecting, right? Yeah. So it doesn't make it wrong, it just makes it not a complete model, right? Gossett says it's like I'm zooming in on a particular part of the universe, okay? So our model has to have at least this many things, but I'm not claiming that this is all that we have. You guys see that distinction? It's a little bit subtle. Yeah. Okay, so let's start making some facts. Now there are some things which are really obvious from the picture, but let's just show how we can, so the kind of thing to do once you become an expert on this is to recognize that immediately upon populating your universe with certain structures, like in this case with lines, I just invented 6 lines, right? So right away, state all the possible things that you can about those lines. And so for example, P1 and P2 are on line L1, right? Mm-hmm. So since that's the case, but also it's the case that P1, P2, and P3 are not collinear, what can I immediately say? P3 is not on L1. And also, P1, P2, P4 are not collinear. So not only is P3 not on L1, but P4 is also not on L1. Again, I'm kind of using my picture as inspiration, but you see how it follows exactly on a technical level from the statements at the end. Okay, and we can just keep doing this. I think there's a whole bunch more of these, so we can go kind of fast, right? Take the next pair, take the next line, like L2, right? So what is L2? L2 is P3 and P4. Well, since P3 and P4 are on L2, and the 4 points are defined such that no 3 are collinear, then P1 can't be on the same line with P3 and P4, right? Because no 3 can be collinear. So immediately I can state that P1 is not on L2, and also P2 is not on L2. Are you guys getting the hang of this? Can I go faster? Okay, it's a little boring, but it's good kind of practice. So let's take the next line, L3. I mean, I'm going to basically do this 4 more times. Go through each of the lines as we've introduced them. What is L3? By definition, it's P1 and P3. And if P1 and P3 are on L3, then P2 isn't, and P4 isn't. If, since line L4 is P2, everyone just finish this at your own pace. Okay. A little bit boring, very rigorous. All right, what I now know is precisely which points are on precisely which lines for all the lines and points I've introduced so far. Cool? All right, now there's another thing that's sort of obvious from the picture, but I haven't yet proven, which is probably going to be really important and valuable to take a minute to prove. What is that? What's a thing that you, just from looking at the picture, you feel is true, but yet we haven't explicitly said yet? The lines are distinct. Yeah. That's when you know you're doing serious math, when you're spending half your time proving that shit is distinct. Alright? So that's what we're going to do now. So why are these lines distinct? Can you think of a reason why, for example, lines L1 and L2 are not the same line? Because they don't have the same points. Is there a particular point you would like to mention?
P1.
P1 say, right? So now what you do is you're like, yo, P1, you are on L1 by definition. But, as we have just proven, P1 is not on L2. Thus, L1 is not equal to L2. Okay? And then we just kind of, let's do one more. Someone else, let's all go around the room and do one. Brass will do one.
P2 is an element of the line, so.
P2 is on L2. Wait, what did you say?
Wait, just kidding. P2 is an L4.
P2 is on L4.
And P2 is not on, what's your favorite number? Like, maybe L3.
Brass will just do one.
L3.
P2, however, is not on L3. Fact. Therefore,
They're on the same line.
L3 is not the same line as L4. Okay,
Stuff.
I'm going to just now write etc. Is that okay?
Yes.
Okay, etc. How many of these are there? I think there's like a bunch. There's like 6 choose 4 of these, right? Because for every 2 lines, I need to prove that they're distinct. So I have 6 choose 4 equals 15 of these statements. All right, now I'm like really happy. Because now I've fully, explicitly, rigorously justified that there are these 4 points, guaranteed by FPP3, that generate 6 lines, all the points are distinct, no 3 points are collinear, I know exactly which point's on which line, and I know exactly that all the lines are distinct. Yes?
Is there like a more elegant proof? Or
No.
Okay.
I don't think so. The more elegant proof is just skipping all the details.
Okay.
But I think the details are valuable, at least at the beginning.
Okay.
Okay. Alright. I think it's time to start the proof now. So, what the hell are we trying to prove? We are trying to prove that there exist 4 distinct lines, no 3 of which contain a common point. So I'm going to write that in a kind of quantifier language. What we need to show is that, wait, what? Oh, what? Oh yeah, we need to show that there exist 4 distinct lines of through. Okay, so I'm actually going to write even an extra quantifier. I'm going to say for all possible finite projective plane models. This is what sort of like, this is sort of what FPP3 prime says. That for all possible finite projective plane models, there exist 4 lines such that there are not 3 of those lines which have a common point. So there exist 4 lines such that there does not exist 3 lines with a common point. With a common point.
Wait, are we proving
Wait, that's
FPP3?
Yeah, did I just screw up?
That's no good.
Wait,
Because they
there
have to
for
be
all
the same.
wait, hold on, chill for a second. For all finite projective plane models, there exist 4 lines such that there do not exist 3 of them. Wait, I think I'm doing this right, right? There exist 4, now it's right, yeah? Okay.
Wait, we're
Yeah.
proving FPP3.
We're just proving FPP3 prime.
Yeah.
We're proving FPP3 prime, right? I'm just writing out a quantifier language.
The 4 lines need to be distinct. We're like kind of doing that last class.
Yeah, we were kind of, so far we haven't done anything really new, except we were just a lot more careful over here. Yes?
Wait. I'll ask him.
Okay, good. Alright, so how are we going to do this? We're okay. Yeah.
Wait, so sometimes when you like write quantifiers, like right after like one quantifier, you want to like say some stuff about the thing that you just quantified and like say like only when this is true. But like other times, like now, you just like put another thing that you're saying is true. How do you like distinguish between which is which?
Okay, hold on. Don't understand what you said, but I want to move on.
Yeah.
I think is this okay for
Yeah.
now? Logic, next
Yeah.
time. Okay. Alright, so what we're going to do is we are going to, we need to do it by contradiction, right? So suppose not. So suppose that this theorem is false. If this theorem is false, it must mean that there exists, I think I was supposed to do this at the beginning. Oops, alright. That there exists some finite projective plane model out there such that,
All 4 distinct lines.
and now I'm basically, I'm factoring the negation through this giant weird quantifier, right? There exists, so put a not in front of this, because that's what we're basically doing, right? So if the FPP3 prime says that for all finite projective plane models, blah, 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 then if the not of that, then there must exist some finite projective plane model such that it's not the case that there exist 4 distinct lines. In other words, therefore, so for all 4 distinct lines, in other words, for any 4 distinct lines, then there do exist 3 of them with a common point. Okay?
No, but
Alright, and what I need to do is show that this leads to a contradiction. That there could be a finite projective plane model where this is true. Well, so let's just, so we're essentially supposing that this is true, right? But every single finite projective plane model, by this kind of intro argument I just gave, must have points and lines that are like this, right? Okay, so what I now know is that for any 4 distinct lines, this must be true. Well, if this is true for any 4 distinct lines, how about our 4 lines? Right? So what I'm gonna do is, okay, well, take our set of lines L1, L2, L3, and L4. This is what we did last class, but I think I'm being a little more clear this time, or I hope I am.
Wait,
Yes.
so like all this proof really is just building a model of it and then saying, well, look at our model and it doesn't work. And that's just
Right. I'm trying to prove that in any model there are 4 distinct lines, no 3 which contain a common point. So I'm assuming that that's false. So then there must be a model in which there are for any 4 distinct. I think you get it, right?
Yeah, but
So now I'm saying, well, take these 4 lines. I'm building a model. These 4 lines must exist in any model. So take these 4 lines. What do we know? So by our assumption, what do we know about these 3 lines? About this set of 4 lines? Yeah, 3 of them 3 of them have a common point. Okay. Which 3? And the answer is it doesn't matter, right? Because the system is totally symmetrical. So now we throw in a without loss of generality. Let L1, L2, and L3 be the 3 of them with a common point. Okay. Is everyone okay with that? Right. 3 of them must have a common point. It doesn't matter which 3. So let's just call it L1, L2, and L3 that have the common point. Okay, and let's call the common point P. Call the common point P. All right. So now, what do we know? We know that there's some point P which is on L1, that also that point P is on L2, and also that point P is on L3. All right. Somehow, this is going to lead to a contradiction.
It doesn't matter which point you pick, right?
Well, I'm being sort of abstract by not saying what the point P is. I'm just, because our assumption has led us to the conclusion that there is some point, I don't know what its name is, right? But that kind of brings up a certain issue, which is P might be one of the points already labeled. It's like unclear, okay? So, why is this a contradiction? Why can there not be a point that's on L1, L2, and L3? Perhaps it's a good idea to draw a little side model over here with just the things that we're talking about at this particular moment, right? So the only 3 lines that are under discussion are L1, L2, and L3. So let's draw that line. Here's L1, here's L2, and L3 is the intersection of L3 intersects L1 at P1 and intersects L2 at P3. Did I do that right? Yeah. We did that already. I just sort of redrawing the picture without the things that kind of messy. Yeah.
Wait, over there, there are like pairs of 3 lines that all intersect at one point. So how can you say that those ones aren't that pair?
Okay, yeah. The logic is very subtle. Okay, so it's actually probably best if I just like started with this and then kind of did that. So maybe just to backtrack it one more time. I'm showing that in any model, there are always going to be 4 lines, no 3 of which have a common point. Okay? That doesn't mean that no 3 lines have a common point.
But
it means,
but
wait.
okay.
It means it's possible to find 4 lines that don't have a common point.
Okay.
Okay, and so now I'm supposing that that's false. If that's
Yeah.
false, then any 4 lines which I pick whatsoever, 3 of them must have a common point. Okay, so now what I've done is I've invoked FPP3 to populate my model with 4 points. And by FPP1 and 2, there are lines through every 2 points. And by our argument, we've shown that the points and lines have this relationship. My assumption, which I hope is going to lead to a contradiction, says that any time I take any 4 lines, are you getting it now?
Yeah.
There are 3. There are 3 with the common
I
points.
thought they were like really specifically L1, L2, L3, L4, but they are.
They are.
Okay.
Right, this is where I'm being specific. I'm allowed, by my assumption, to take any 4 lines. And my assumption is that any 4 lines I pick, this is pretty hard,
Right, but
any 4 lines I pick must have a point in common.
right, but you can't pick the point the same way because of the fact that
Right, so,
right.
you with me now? Okay, so I specifically chose L1, L2, and L3, and L4 because they don't have this property. Okay, so now I have my, and then from that, my assumption, which I hope leads to a contradiction, is that 3 of these lines have a common point. And now I'm saying, well, as the lines are all symmetric, I'll just take these 3. Suppose these 3 have a common point. Okay, so I'm waiting for the contradiction, or I can just maybe do it, yeah.
Isn't there like a contradiction from FPP2? Because FPP2 should say that L1 and L2 only intersect with P, and L2 and L3 only intersect with P. Therefore, L1
Yeah. What's the problem with P? Let's talk about what P is. Could P be? I think you only need to do this once, right? So we can show that P is not P3. Why is that true?
Because it's not on the line L1.
Because it's not on L1. Yeah. P is on L1 because we defined it as the intersection of L1, L2, and L3. But what's not on L1? P3. Since P3 is since P is on L1 but P3 is not on L1, I can state emphatically that this weird point P, where all three lines intersect, is not P3.
So do you just have to go through and do that?
I don't think I need to do them all, right? Because now, since P is not P3, what I have is, this is kind of what Eob was saying, what I have now to add to my picture is I have L1, L2, and L3 all intersecting at some point P. But that's impossible, because, because P and P3, P and P3 are on L2. And also L1.
Yeah, you can,
Oh.
right.
Right?
Oh.
Yeah.
I see.
That's the problem, right?
Yeah.
So lines are sets of points. So what we have now is that P and P3, that set of points, is a subset of line L2. That's just kind of my technical way of saying, L2 contains those 2 points. There might be other points on L2. So L2 has P on it, but L2 also has P3 on it. But then also, P and P3 are on L1. And the key here is that I showed that P and P3 are different points. You can't have two, and I also have that L1 and L2 are different lines. And what I've just shown is 2 different lines which intersect at 2 different points. This is impossible. Oh, so I'll just write that. If P and P3 are on L2 and P and P3 are also on L1, but L1 and L2 are not equal, this is a contradiction with FPP1. Who is with me?
Yeah.
I think I can do a little bit better with this picture. Let's see. Did I even possibly label something? So P2 is over here. So the way to think about it geometrically is to say, look, L1 is the line through P1 and P2. L2 is the line through P1 and P3. And now, supposedly, there's some weird point P out there, which is on L1, L2, and L3. But it's just impossible for L1 to
Yeah, it's like,
where is it across?
no, it's the second axiom, it just says that's just it. If you're saying the lines are distinct, they can only contain one common point. But we proved that P is not the same thing as P3.
Yeah, I guess you can think of it either way, right? Any 2
Yeah.
distinct points, P and P3, can only be on one common line. I think it's
It works
FPP1.
with both of them.
Yeah, it works. It's a contradiction with both of them. Yeah,
Yeah.
I agree. Okay, wait. I had a sort of visual way of thinking about this, but suddenly I'm not finding it. The problem with this is, well, anyway, there's the proof. Okay, so wait, so my contradiction is my contradiction with this assumption that our assumption was that 3 of them have a common point, but that leads to a contradiction. So okay, this is proof. Who feels like they get this? All right. So we can either, this is what I wanted to finish last class, that didn't happen. So I can either give it for homework, or we can take 10 minutes and do it right now. Another proof which is in the same family, which is essentially proving FPP3 from FPP3 prime. Sage.
Wait, I have a question about that picture. So in your final statement, you said like PP3 is part of L1, but like how is P3 part of L1 in your picture? It's like,
Oh, wait.
Wait,
In
did I
the
do something
previous
wrong?
statement, you said PP3 is not an element of L1. And then you said
P3.
later that it is.
Wait,
Oh,
hold
just
on.
make it L3, just make
yeah,
it
that's
L3.
what I'm saying.
Should this
I
be
think it- I
L3?
think it should be
Yeah, yeah.
L3.
Oh, yeah. Wait, yeah, something was weird there. Okay, wait. PP.
Yeah, that's, yeah,
That's true.
yeah.
Okay, so wait, maybe now I can go back and do my intuitive thing again, because I was confusing myself. So what I want to show is that L2 and L3 are not the same. And why can they not be the same? Because there's this point that's on all three of these lines. Oh yeah, so here we go. So if there's a point that's on all three of these lines, and that point is not,
Because you don't.
You don't need to like consider like a third point.
oh yeah, wait, maybe it's like even simpler than this, right? There simply just can't be a, well, oh, okay. Maybe it sort of works better if you actually don't try to draw the picture, because P doesn't exist, so drawing it's kind of like weird. So anyway, but yeah, that's better now, right? P and P3 are on L3. P and P3 are on L2. P and P3 are different lines because P3 is not on L1, but P is on L1. Okay, yo. Do you want to try this for homework, or do you want to take 10 minutes and do it now? I could go either way.
Yeah, it's the exact same, it's like
From last class? Oh,
No,
it is,
it's- it's
so
a
yeah, so,
duality.
okay,
Yeah.
so Ethan says, yo, isn't by duality, isn't this essentially the exact same proof? Yes, so it's kind of like an exercise for you guys to like do
for
it.
word this thing.
Okay, he's like, it is
Yeah.
word for word the same proof. It is very similar. It's like extremely similar. To the extent, yeah, so it's one of those things where like you might think it's trivial, but for other people, I mean, it's essentially like doing this over again, but it's different enough that it's a new thing. I think we should do it. Let's say everyone take 5 minutes and just do it. You can skip some steps and stuff, but like I think it's valuable, because you were just watching me and you're like, oh yeah, I get it. But no, you probably didn't. So does everyone understand what we're doing? We're showing that FPP1, FPP2, and FPP3 prime imply FPP3. Which means that we could have taken either of those two as axioms, and that fully proves the duality.
Wait, how does that? Because two is happening to you as that. Well, how does that necessarily mean?
Well, if I think the argument is were to just add FPP3 prime as an axiom, then duality holds, right? What if I just